All right. Let's continue where we left off, but before we continue, again with the first lab, if you had completed the lab in lab or shortly after lab, you have your labels. Just submit them this week. By Friday, make sure you have submitted your labels if you have already completed the exercise. You need 5 labels, including the cookie. If you have done an extra credit, submit it to get the +2. Why not? So you'll get your 25 points by just submitting your labels and +2 if you have done the extra credit. Now, who has not had access yet to the program?
I can help figure that out for you. We can schedule a time to.
So Saj, you sent an email already to the people, the 7 people that.
For the remaining 5 people, 2 of them back to the.
Okay.
Don't speak up, I'm assuming you got access.
Please complete your, if you still have problems, let us know. Otherwise, we're gonna assume everybody had access to the program already. So we need you to complete that and get this out of your way so we can continue with lab life, right? If you have issues, make sure you let Saj know. Yes, Rachel.
Last time. Put this on that, labels in, it's still saying lab report as mission section, not.
Saj, make sure Brittany changes that to labels.
But it's the same thing, it's gonna be just the same submission spot.
Submission spot, it will say labels, nutritional
But
labels, and
I already submitted mine under the lab, that's not.
it's fine. If you submitted, it's accounted for. All right, so Brittany will send a note if she wants to keep it the same name because it messes up the grading book. Just submit it to the lab report assignment, but submit just your labels. Because we just worry that it might mess up the grade book if we change the name. Okay. All right, so if you have any questions, let us know. All right, pull out that same piece of paper that you started last time. If you lost it, start a new one, write your name. We didn't go very far other than this. So it's okay if you start a new one. Okay, so we were going over some calculations, refresher to how we use those different equations as they apply to preparation of reagents and buffers. Okay, so we had this exercise with 0.1 normal HCl. Let's continue the calculations practice, okay? I need you all to be doing this, okay? All right. Calculate the number of moles of calcium in 25 grams of calcium chloride with 2 molecules of water. Okay, so I'll write down some given here that you need, okay? So number of moles, what's the equation for number of moles? Can you see this? Yeah.
Mass, not a mole mass?
Thank you. Mass in grams divided by the molecular weight or molecular mass in grams per mole. And this unit is mole. Oh, I don't know how fast we can go and you can still see. The units for number of moles is mole. All right. So you need this equation. You need to also know the molecular weight of calcium is, does anybody remember? 40, yes. 40 grams per mole. What is the molecular weight of what else is in there? Chloride. 35.5 grams per mole. What is the molecular weight of oxygen? 16. And hydrogen? 1. All right, now we can solve. Anybody get? Yes. 0.17 moles, correct. So basically, you just add up the molecular weight of the individual elements. It comes out to 147 grams per mole, the molecular weight of the entire molecule. And since we have 1 mole of calcium, so the number of moles of this molecule will be equal to the number of moles of the calcium element. So molecular weight, mass divided by the molecular weight, and then the units cancel, then we end up with 0.17 mole. Always put your units so that you know that your equations is correct and your units cancel to get to the final unit. Okay, just remember that rule. If you put your units, you will know that where you're gonna get with that. All right, let's do this. Now you want to prepare 1 liter of 0.2 molar NaOH from 2 stock solutions. The first one, you have a stock solution of 3 molar NaOH. How would you prepare from that stock solution 0.2 molar? Or you have a stock solution that has 45% weight by volume as a concentration. Now, what you need to solve this is, so you know what 45% means, right? And 45%, when we say weight by volume, this means 45 grams per 100 milliliters. That's what it means, okay? That's one given. The other given that you need, what's the molecular weight of sodium? Does anybody remember? 23 grams per mole. And then O, we already have the O, we have the H. Okay. And then molarity, you need to remember molarity equals what? What's the equation for molarity? Yeah. Number of moles per volume, and the unit is mole per liter, 1 liter, okay? So this is important. And 1 liter is how many milliliters? 1,000. So you need all this given. So now solve A and then we'll solve B. The first one. Anybody has the first one? You need to remember this as well. For the first one, you need to remember that volume times concentration equals volume times concentration at equilibrium. So you use that for the same example we used for the HCl. The same equation we used for the HCl itself. Yes.
66.6.
66.7 if we round ml. Okay. So we need 1 liter. So let's put it in milliliters, 1,000 milliliter. And we need 0.2 molar. What is the volume in milliliter that I need to take from my stock solution that is 3 molar? So it is solving for X. So this over 3 molar, your units cancel. This gives you 66.7 milliliter. So what do you do with that? So always complete the question in an exam or quiz. You get the volumetric flask, you put water in there, always water first. DDW, double distilled water, or deionized distilled water. And then you add your 66.7 milliliter, and then you make up the volume with water. Or DDW, same, so that don't confuse you. One liter volumetric flask. Okay. That's the first one. Now solve the second one. You have this, I can erase so that I can. Anybody? Writing? I'll wait for a second. Anybody that reaches an answer, raise your hand.
For stock solution for blue, 17.8 milliliters per liter.
Very good, 17.8. Did anybody reach that same number? Okay. All right, we'll go through the calculations together. All right. I'm gonna erase this. Okay. So the very first thing you want to do is unify your units. You need to prepare 0.2 molar, and you have 45% NaOH. So the first thing you want to do is calculate the molarity of 45% NaOH. Okay, so that is the first thing you do. Unify your units, and then you can apply the equation, and M by V equals N by V. So to unify the units, this is my given. Okay, so molarity is in 1 liter. So the first thing I want to know is how many or how much is the weight or the mass per 1,000 ml, because I have it here as percentage per 100 ml. So what would be the mass in 1,000 ml? Who got that far, Razi?
450 range?
Yes, so we have 450 grams in 1,000 ml. That is my stock solution. All right, next, I want to get the number of moles so that I can get molarity. I have the weight. So let's go here. So I have the weight. I can get the molecular weight. Then I can get the number of moles. So the weight is 450 grams. The molecular weight is NaOH. What's the molecular weight? 40, yes. So we got 40 grams per mole. So the grams cancel, the mole go up. And then what is the divided by 4? What is it? 12.5? 11? 0.25. Okay. Yeah, well, first it is moles, right? So it's moles. And then when we put per liter, because 450 grams is per liter, so my molarity equal number of moles per liter, so it is 11.25 moles per liter. 11.25 molar. So now I can apply the equation of solving for X milliliter from my stock solution equals, I want 1 liter, 1,000 ml times 0.2 molar. So X milliliter equals molarity cancels. What did we get? 17.8 milliliters. So same thing, you get your volumetric flask, you put some water in it, put 17 milliliter from your stock solution and make up the volume with DDW. You can take a picture of that if you want, or if you have the calculations already on your paper, make sure you take a picture of that before you hand it in. Any questions? Anything you would like me to clarify? Don't, make sure I'm not in the picture. Don't post it on your Instagram or Facebook. No, just kidding. Okay.
Question on the first.
Huh? Yeah.
So
Yeah.
I know it's got 20.7 moles, but isn't the question asking for like the moles of calcium specifically?
Yes, but you have one calcium in the entire molecular weight. So number of moles of the entire formula is equal to number of moles of that calcium. Because the ratio, yeah, that you want to remember a little bit your general chemistry by when you let's go back to this. So if you look here, you have 1 mole of calcium, you have 2 molecules. So you have 1 molecule of calcium, 2 molecules of chloride, 4 molecules of water, and 1 molecule of oxygen. So 1 mole of the entire formula is equivalent to 1 mole of calcium. Because 1 mole of calcium is relative to its molecular weight. Its mass relative to its molecular weight. So when you correct for the molecular weight, number of moles will be equal. You have, okay, you're not envisioning that. That would be a lecture in chemistry that I will talk to you later about it. Yeah, so it's just you want to go back to a little bit of the basics of how you determine equivalence, but we can talk about it after class, okay? Yeah. All right, any questions about this? Okay. Right? Now it's a little bit more complicated question. I'm going to erase this for now. Try to think about it, and then I will write the given for you. Okay. So you have a concentrated H2SO4, and it is 98% volume by volume. Okay. We have density equal 1.84 grams per milliliter. We want to unify the unit. I want to prepare 0.1 molar. So I want to find out the molarity of this concentrated solution. That's the first thing you want to do, because then it will be easy after that. Unify units and then get the volume you need from that stock solution. Anybody had an idea of how do I go about this? Why am I given the density and what I need? Yes, Graham.
90% on so here's 100.
Yes. So this is actually 98 milliliter of H2SO4 in 100 milliliters. So what you want is, since we have a density, what's the 98 milliliter in grams? What's the weight of that? So since I have the density equal mass by volume, and I have the density, so I have 1.84 grams per milliliter equals X grams, I'm solving for that, over 98 milliliters. So what's the X? X equals, yes, right,
180.32.
180.32
.32.
grams. All right, so this is canceled. And then your value will be in grams. Now this is in 100 milliliters. What do I need to know? In 1 liter, right? So this is, so now I have 180.32 grams in 100 milliliter. How much do I have in a liter? 1803.2 grams per 1,000 ml or per 1 liter. Okay, so now I have the weight. All right, so I need the molecular weight of H2SO4. So let's see, down here, sulfur is, molecular weight of sulfur is?
Right, you gave it to us on the, it's 98.
Oh, I did? Okay,
Yeah.
well, sulfur is 32, oxygen is 16, H is 1. So we get a molecular weight of 98 grams per milliliter. So now I apply this. So I have the 1803.2 grams divided by 98 grams per mole. What do I get? So grams cancel, mole goes up. What's the value? Anybody with a calculator? Say that again? 1.84?
18.4.
18.4.
18.4
Yep.
moles. So molarity then because it's moles per liter and we calculated amount per liter. So the molarity is 1 mole. All right, so now you apply the same situation, M by E equal M by V. I need 500 milliliter though this time, not a liter, not 1000. So your equation would be M by V equal M by V. And then you have the molarity of your starting solution, 18.4 moles per liter times X milliliter. And I want, what do I want? 0.2, right?
0.1.
0.1 mole per liter times 500 milliliter. Okay, so units here cancel. And then I divide by 18.4. So 50 divided by 18.4, 2.7. 2.72 and 2.72 ml. Same deal. Get this time volumetric flask that's 500 milliliters, not 1 liter. Make sure you remember that. You add a little bit of water, you put your H2SO4, and you make up the volume. And you can take a picture. If you have it on your piece of paper, take a picture of your piece of paper. Any questions here? Yeah, so these exercises are not in vain. Trust me, if you're ever in a lab responsible to prepare reagents, you really need to order reagents, see what the bottle says, and then go through all these calculations. So it's good exercise. All right. Any question? I can repeat. It's okay. Okay, I will leave that for a second. Let's see what's coming next. This is a dilution equation. So almost every time you want to calculate concentration of a component, you need to dilute, especially if you're doing spectroscopy methods. You will have to dilute to be in the linear range. And this is an example of diluting to fit a standard curve concentration. So you need to take 2 ml of the sample after you dilute it. And then you have a stock solution of 16%. So let's put again the given. Think about it. All right. Let's put the given. Method requires, so required volume is 2 ml. So you want 2 ml of the diluted sample. You have a stock solution of 16%. So this is 16 grams in 100 ml. Okay, So you want to prepare your standards. Okay. So you need standard concentration of 0, that's your blank, 0, okay, I have short-term memory loss, 0.1, 0.2, 0.3, and 0.5 milligrams per milliliter. All right, so this is so that you take 2 milliliter of the standards, the diluted standard, to prepare your standard curve. You'll be doing some of that work for the glucose assay that we will do in the lab. We will have to dilute the standard and then dilute the samples and then take 2 milliliter of each. Okay, what's the very first thing you need to do? Step 1. Your stock solution unit is what? 10%. And then you need to dilute, what's the unit? Milligrams per milliliter. So now I need to convert. So the first thing you need to do is convert. So what's 16% in milligrams per milliliter? 160. You already did that. Very good. So this is basically you have 16 grams in 100 ml. So you divide by 100. So 16 grams divided by 100 ml. And then how many milligrams are in grams? In 1 gram. Right? So you and then 160 milligrams per ml. Okay, I want you to take a moment and then see what next. Now your stock solution, you'll have that concentration of your stock solution. Now what do you do? Simple, we've been doing this all along. What's the equation that you would use for this dilution? We've been using it in all of the other. Concentration times volume equal concentration times volume, right? Let's do that. So concentration, no matter what the concentration is, doesn't have to be molarity, it doesn't have to be normality, it can be percentage, it can be milligrams per milliliter, as long as it's a concentration. Concentration times volume equal concentration times volume. So I want to prepare 2 milliliters, right? So my volume is 2 milliliters that I want to prepare. And one of my concentrations, the first one is 0.1. So I need 2, well, concentration is 0.1. So 0.1 milligrams per milliliter times 2 ml equals the original concentration, 60 milligrams per ml times X milliliters. All right, so please. Let's see. I need people to speak up that haven't been speaking up. Get a basic plus two.
0.0015.
0.0.
0.2.
Oh my goodness. What is that in microliters? Is there any pipette tip that you can use to dispense 1.25 microliters? No. Well, even if we haven't in this, it's so hard to get a 0.25 microliters dispensed. It's less than a drop, less than a teensy tiny drop. We cannot do that. So what do we do? Who works in the lab? Come on, Graham. Scale up? I mean, you're on the right track, but we don't call it scale up. What do you?
Serial dilution.
Serial dilution. So instead of scaling, preparing, what did you mean by scale? So you add a higher amount and then you dilute, right? Okay, so but we take the stock solution and we do another step dilution. That's what, I'm sure that's what you meant, but we call it step dilution.
I mean, I was wondering if you can do either 1 mil
So
or 99 mils.
those of you that work in the lab, what would be a comfortable amount to dispense? Are you able to dispense 125 microliters? You could, but to make it easy, to make the math easy, you can dispense 125 microliters using 200 microliter pipette. Okay, so this 125 is 100 times more concentrated than what you want. Correct? Are you following? So 125 is 100 times more concentrated than 1.25. So what do I do? If I want to reach this, if I want to be able to get 125 microliter of my solution, add to it enough to make it 2 milliliters. What should I do with my stock solution? Diluted how many times? 100. So I dilute my stock solution by 100 times. And then I can take 125 microliter. Can you suggest how I can dilute? So basically 100 times, that means I want to prepare a solution of 1.6 milligrams per ml. How much I would take? You would do concentration times volume equal concentration times volume. You would know how much to take from this to prepare a solution of 1.6, which is 100 times less. And then once you have this serial dilution, then you can take 125 microliter from it. Here's all the calculation. Please make sure you write it down. If you have questions, I can repeat. But the gist of it is that you cannot withdraw 1.25 microliter. So you select a volume. For ease of calculation, we said 125 instead of 12.5. It's really hard when you have a fraction of a microliter. It's very hard to dispense. So 125 we could dispense using 200 microliter pipettes. So this is 100 times more concentrated than what I want. So I go ahead and dilute my stock solution 100 times. And that's that. Any questions? We are gonna practice dilution problems for next lab. So, but this is just give you kind of an idea. All right. If you have a question, you can ask. In the last few minutes, we can talk about it, or I can move on. Go ahead.
My sheet of paper is full. They're gonna send me a sheet of paper. They're gonna do another problem this night, but
We're gonna do another problem, so you can use another paper. You know, it's a good question. We have a couple of other problems, so keep your papers with you until we're done with this lecture. Okay, so in the last 5 minutes, I'm just going to introduce buffers really quick. And then the next couple of equations will be related to producing or preparing a buffer. We can do these calculations next time, but just to get you started. So we talked about buffers last time being a mixture of a weak acid and its conjugate base. Do you remember what the conjugate base is? You remember another name of a conjugate base? Go ahead, huh? What base? No. And okay, it's okay. Huh? Yes, dissociated. So let me erase this and remind you of an easy way to think about it. We talked about it briefly last time. Okay, so an acid, we give it the letter A, and an acid usually has a proton. So AH is your acid. And then when the acid loses the proton, it becomes a minus. So that's your conjugate. Base. Or it's also called dissociated acid. Or it's called the salt. So you can hear it in multiple ways. But a buffer contains both. You have both in the buffer. And it's buffer, meaning it is it resists change in pH because you have the ability to give up a proton if you're titrating with a base, or if you're titrating with an acid, you have the ability to pick up a proton. So you always the pH is adjusted or resist change. So that's the first couple of points here. And then Henderson-Hasselbalch equation, you will need it. You will need, you need to remember it for solving buffer equations, which is the pH. What is the pKa definition? If you want to look at this equation, try to remember pKa definition. What is it? Literally, look at this equation and define pKa. What's log of 1? 0. Okay, now define it, Tyler.
I think it has to do with the evaporative density of the water.
You know, don't think too deep. Look at the equation and tell me. Wait a second, Rob. Let me see for other people and think about it. I gave you a hint. Log of 1 is 0. It's right there. The pKa is the pH at which you have equal concentration of acid and conjugate base in the system. That's what the pKa is. So the pKa equals the pH. When you have log of 1, it's 0. When you have equal concentrations, you have log of 1. So that's an easy way to either remember the Henderson-Hasselbalch equation or to remember the definition of pKa. All right, so this is important when we try to figure out how to prepare a buffer. We need to know the pKa of the acid, and we need to know what the pH that we want to prepare. Then we can determine the how to prepare the concentration. And another thing to keep in mind as hint, the concentration, if we say 1 part, because the buffer is a combination of acid and base, conjugate base. So 1 part of the buffer is equal to the concentration of these two. So 1 concentration unit, whatever is the unit, is equal to this plus this. Or if we're talking about 100%, because it is, you combine them. So 100% is both of them together. So 100% also equals this plus this. So it's either 100 or a 1 unit of the concentration, because the buffer contains this and this. It's not always equal parts. It's not always 0.5 and 0.5. When it's 0.5 and 0.5, you have the maximum buffering capacity. Remember that. When the concentration is equal to each other, you have maximum buffering capacity. Okay. I will leave you with this happy note, and then on Friday we'll do some calculations. You can take a picture if you wish so that you remember how to solve the problem on Friday.
Class.